We're nearly done with this page. We were looking at this simply supported beam and applying the energy method to determine the collapse mechanism. So we set up the equation for external work. That's the applied force times the distance through which it acts, or the deformation that is associated with it. So in this case, it's the force times the vertical displacement. If we had a moment instead of a force, it would be the moment times the rotation associated with that point. So we'll look at examples of that later. And then the internal strain energy here is all the internal ultimate moments that occur at the plastic hinge. So we have internal MU at the hinge, and we have the two angles that are associated with each side. As I mentioned, you can also, it may also make more sense to you if you think about the total, the best way to draw that, the total rotation at the hinge is theta 1 plus theta 2. So that total rotation times the total moment, mu, at the hinge. Either way, you end up with 2 mu theta for the internal strain energy. And now we're ready to apply the total work principle. So setting the internal strain energy equal to the external work, we have Pu times theta L over 2 is equal to 2 mu theta. So solving for Pu in terms of mu and L, we have Pu is equal to 4 mu over L. And then plugging in the term for mu in terms of the cross-section geometry and yield stress for this rectangular cross-section, we have 4 over L times BC squared times the yield stress. So that's redundant. So I'll just note here that this is the value for Pu to cause collapse. So now that we have checked or determined that using the energy principle, right? Because in the previous page I said the approach we're going to take in this class is to use the energy method to determine the collapse mode and then confirm it with equilibrium. So now that we've determined the collapse mode, we will confirm with equilibrium. So looking at the collapsed state, we'll break the beam into 2 segments. So we have, I'll call this side A, call this B, and this C. So we have the reaction forces at the ends would be each Pu over 2, since it's symmetrically loaded and supported. That distance between, the horizontal distance between each point of interest is L over 2. And we have our ultimate moment, mu. And can't forget about the applied load, Pu. All right, so if we just take the right side of the hinge, and some moments about B, we have mu minus Pu over 2 times the moment arm of L over 2, which is equal to 0. For equilibrium to be satisfied, right, that has to be equal to 0. So what we're doing is we're using that and proving that we get the same result. So PU is equal to 4 mu over L. And since that matches the result that we got from the energy balance, then that confirms that this is the collapse mechanism. Now, of course, this was a simple case because it was a simply supported beam. There's really only one way for it to fail. But in the next lecture, we'll apply this to some more involved situations. So, as noted down here, results will be different for other cross-sections, right? Because this was all developed based on a rectangular cross-section shape. So if you have a non-rectangular cross-section, right, this relationship will be different. So you have to keep that in mind. So a recap of the process before we move on. Right, based on the material and the cross-section shape, you'll find the ultimate moment. And then you determine the failure mechanism and calculate the ultimate load using the energy method, then confirm it with equilibrium. All right, so the next lecture continues this concept, of course. And remember that we are operating based on the assumption that the elastic energy is much smaller than the plastic energy at failure. So based on that, we've been saying we're going to ignore the elastic energy and just focus on the plastic energy. So the process. All right, well, this is kind of redundant because we just did this, but you know, this is intended to be a new day right here. So determine ultimate moment, and then also corresponding PU or QU, etc. Whatever applied loadings you are considering, you're going to want to know what they are, what the value would be to cause collapse. So that's your ultimate load. And then solve for the collapse mechanism. Now, for determinate beams, like the one we just looked at, the collapse will occur once one plastic hinge has formed. That's all it takes. For an indeterminate beam, you need to consider multiple modes of collapse. All right, so there's more than one hinge that will need to form for an indeterminate beam to fail. And so you have to figure out, well, which hinge is going to fail, which hinge will form first, and then, you know, what are the different possible mechanisms that could result from all the possibilities based on the loading and the configuration. So we just looked at the simply supported beam, so I'm just going to really briefly recap the values that we found, right? So mu we found to be for the rectangular cross section. Mu was BC squared times the yield stress. The work done was Pu times delta. Internal strain energy was 2 mu theta. And delta was equal to 1/2 theta L. All right, where that mechanism looked like this. And from that, all right, we got Pu is equal to 4 mu over L. Or 4 BC squared times the yield stress over L. So again, this solution is specific to a simply supported beam with a point load at the center and a rectangular cross-section. If we consider now an indeterminate beam, so changing the left support from a pin to a fixed end, still having a point load at the center, right, mid-span, let's consider the moment diagram. So for the elastic condition, right, the elastic moment diagram, you're going to have a moment reaction at A, and it's going to be a negative moment. And then at, we'll mark that as B and that as C. At B, you're going to have a positive moment and no moment at C because it's the roller support at the end of the beam. So say that's A. That's going to be your MA, that's your MB, so that's M, X. Here, the moment at A is greater in magnitude than the moment at B. So that tells us that the hinge will develop first at the fixed support. Right? But collapse won't occur until the second hinge forms, which will be at point B. So the collapse mechanism, right? Once the hinge forms at A, right, you have ultimate moment developed at that location, but it can no longer resist any additional moment, right? It's reached its max. So plastic hinge has formed. It's essentially behaving as a pin support at that point. And then you keep increasing the load though, right? So you keep increasing the load until the moment at B also reaches the ultimate moment. Until that point, it's going to behave as a simply supported beam. Once the hinge has formed at point B, then you have your collapse mechanism, right? And it will look something like this. So again, we have our theta 1 and theta 2, since it's they're equidistant, right? They're going to be equal in magnitude. And we have our moment mu at the hinge. So applying the work principle, we have the total work done is still going to be just PU times delta. And delta, again, is equal to theta L over 2, as before. And again, that's based on small angle theory, remember? And as noted a moment ago, theta 1 and theta 2 are equal due to symmetry. I'll just note that. Theta 1 equals theta 2 equals theta due to symmetry. Internal strain energy will look different this time, though. So now we have two MUs associated with this angle, right? If we consider the segment from A to B, we have MU on two ends times theta 1, and then if we just consider segment BC, we have MU here times theta 2. So we'll say we have 2 MU theta plus MU theta, and that first term comes from AB, and the second term comes from BC. So then setting external work equal to internal strain energy, we solve for the ultimate PU, which is 6 MU over L. So if we have a rectangular cross-section, all right, from the last lecture, we showed that MU is equal to BC squared times sigma y. So PU would be 6 times BC squared sigma y over L. Any questions so far? Okay. So what if we have a distributed load? Similar approach. We're going to first consider the moment diagram. And the elastic moment diagram here for a distributed load, we would have, again, a negative reaction moment at the fixed end. And that's the roller support. Right, it would look something like this, where we would have, do it a little bit. So we'd have a maximum value, a maximum positive value somewhere in the span, but we don't know exactly where. So here we know that one hinge will occur at the fixed end. We need 2 hinges for collapse. We don't yet know exactly where the second hinge will be. Right? When you have a point load, you can conclude that there will be a plastic hinge directly under the point load. But for a distributed load, it's not as straightforward. You have to solve for that location. So I'll say I don't yet know. So we're going to call that distance. I've already sort of noted it on here. We'll call that distance A. All right, so when we have a plastic hinge forming at the fixed end and a plastic hinge forming at an still unknown distance A, our mechanism will look like this. So we'll note, we'll call it A and solve for it. So we have our moment mu occurring at the plastic hinges. And at the left end, we have an angle theta 1, and at the right end, we have an angle theta 2. We can't say in this case that theta 1 and theta 2 are equal to each other. So we're going to keep them in terms of theta 1 and theta 2. Also going to note the distance underneath the maximum deflection at the plastic hinge. Call that delta. And so we can say theta 1 is equal to delta over A, and theta 2 is equal to delta over L minus A. All right, again, using small angle theory, saying that the tangent of an angle is equal to the angle. So our internal strain energy, if we consider just the first segment, we have from that 2 mu theta 1 plus from the second segment, we have mu theta 2. So that's going to be equal to mu times delta, and then in brackets, we'll have 2 over A plus 1 over L minus A. The external work done, since we have a distributed load, right, that equation officially is an integral. So the integral of Q of X, right, this is the general equation for distributed, any type of distributed load. This one happens to be constant, but if Q varied with X, you would have to integrate that function, of course. And then we multiply that by the deflected shape, which is also a function of X. So in this case, because our distributed load is constant, we can bring QU out front times the integral of the deflected shape as a function of X dx. So since our deflected shape in the collapsed mode is just straight line segments, this becomes easy. We don't actually have to evaluate the integral, right? It's just going to be the area under the triangular deflected shape. So we have QU times 1/2 delta A from the first segment, and then from the second segment, QU times 1/2 delta times L minus A. So I'll just note. Oops. All right. Where did it jump me to? All right, jump me to the next page. There we go. All right, we're back. All right, so finalizing this thought, we have our external work is equal to 1/2 QU times L times delta. So to determine the collapse mode, we set internal strain energy equal to external work for our total work principle. So we have 1/2 QU times L times delta from our external work is equal to mu delta, and then in brackets we have 2 over A plus 1 over L minus A. So we solve for QU in terms of mu, L, and A and we get 2mu over AL times numerator of 2L minus A, denominator of L minus A. Okay, so we still have two unknowns. We have right now QU in terms of A, but we don't know what A is. So in order to do that, we will find A, the location of the hinge, by taking the derivative of Q with respect to A and setting it equal to 0. So that would represent the minimum distributed load magnitude that would cause this collapse mode, right? So we want to find the minimum value of Q to cause collapse based on point A. So if we take the partial derivative of Q with respect to A, set it equal to 0, and solve for A, we would get A over L is equal to 2 plus or minus the square root of 2. So looking at this critically, right, we have two options, but since A has to be less than L, right, it has to be within the length of the beam, that narrows it down to which one is correct. So let's see, since A is less than L, that leaves us with A over L is equal to 0.586. So with that information, setting A equal to 0.586 L and plugging that in to our equation for QU, we get QU is equal to 11.69 mu over L squared. So that right there is the smallest distributed load that would cause the moment mu within the length of the beam, all right? So that's the smallest Q that would collapse the beam. Questions? So now that we've gotten our solution from the energy method, we'll use equilibrium to check it. So for this, we're going to, there's a couple different ways you could go about it, right? But I'm going to act as if we don't know QU, all right? And we're going to use this value for A. So we've got our free body diagram now complete with the exact location of the plastic hinge, all right? And we will apply equilibrium to the entire structure. So summing moments about A We get mu plus mu minus mu minus qu times L squared over 2 plus RBL is equal to 0. So I'm just going through and I'm counting all the mu's within the beam, right? And then the moment caused by the distributed load and the moment caused by the reaction at B, about point A. So that's one equation that we have. We're going to need two more to get all of our reactions and check them against, well, I guess we didn't solve for the reactions previously, but we'll use those reactions and solve for QU. All right, so next we'll look at the left side of the hinge. So take the left side free body diagram. We have mu at both ends. We have the applied distributed load, QU. We have the reaction at A. And this distance is 0.586 L. And I'll call this point little a. So we'll look at the left side equilibrium equation, summing moments about the little a. We get negative 0.586 times L and RA plus 2mu plus QU times 0.586 L quantity squared over 2 is equal to 0. So that's another equation that we have. The unknowns that we'll be solving for, by the way, are RB, RA, and QU. And QU is what we're interested in because that's what we have to compare to our energy method results. So then we'll look at the right side free body diagram. So here we have our little point A, mu, reaction at B, distributed load. And this distance is 0.414 L. So summing moments about A, little a, we get negative mu minus QU times 0.414 L squared over 2 plus RB times 0.414 L is equal to 0. So now we have three equations with three unknowns. So solving that system, we get the reaction at A is 6.845 times mu over L. The reaction at B is 4.845 times mu over L. And QU, we get 11.69 times mu over L squared, which agrees with the result we got from the energy method. Questions?
So to get that our A was equal to 2 plus or minus root 2, to then get our A over L, we'd have to take that partial derivative for our QU that we set up. If it was a different shape or like different loading pattern, we'd have to take a new like that's not like a set value. That's unique to this.
That is
pattern.
right. Yeah, that's unique to this configuration and loading. Yep. Any other questions? All right. So next example, we'll consider if we have more than one discrete load on a beam. In this scenario, we could also have more than one failure mechanism. So the method that we're going to apply, right, is the same approach, energy method, and then check with equilibrium. But with more than one load, we have to think about how we're going to get there, right? So we're going to assume that these two loads will increase together, right? So this load is always 2 times the magnitude of this load. And I'll write that down. Assume the loads increase together. So the collapse will correspond to when P is equal to PU and 2P is equal to 2PU. We're also going to assume that we have ultimate moment, mu, throughout the entire length of the beam. All right, the actual collapse mode will have values of mu at the locations where the hinges have occurred, but there will never be a location along the length of the beam that exceeds mu, right? That's the limit. It can't physically develop a moment that's larger than mu. So I'll make a note of that. So we'll actually have a distribution. It's not going to be a constant mu throughout the length of the beam. It has a distribution, moment distribution. With the maximum moment equal to mu. Okay. So for this beam, we have 3 possible collapse scenarios to think about, right? We know we have a fixed end, right? So we know a plastic hinge can form there. A plastic hinge can form here, and it can form here. We only need 2 plastic hinges to form, right? So which 2 of those 3 will form first and be our collapse mechanism? We'll consider the first option, which would be a plastic hinge forming at the fixed end and then under the mid-span load P. So this is the scenario that we previously considered, right? Where, except the difference is now we have another load that will contribute to the work done, right? So it's not going to be the exact same result for the definition of PU. All right, so we'll have a moment mu at the hinges, and we'll have theta 1 and theta 2, and We'll have our delta under the load P, and then under the load 2P, because we have to consider that as well for the work done, we need to know this value. So based on the geometry provided, right, we can determine that this distance is going to be delta over 2. All right, so their work done is equal to P delta plus 2P times delta over 2. Internal strain energy, this is the same as what we saw before, right? So we'll have 2 mu theta 1 plus mu theta 2. And in this scenario, since the internal plastic hinge is mid-span, theta 1 and theta 2 are the same. And we'll also sub in delta divided by L over 2 for theta. So we get our internal strain energy is 3 mu times 2 delta over L. Setting work equal to internal strain energy, we solve for Pu, and we get 3 mu over L. The next scenario we'll consider is if the plastic hinge forms at the fixed support again, but then the other plastic hinge forms under the load 2P. So then our beam collapse mode will look like this. We'll have our moment mu at the plastic hinges. We have theta 1 and theta 2, which are not equal in this scenario. We have our distance delta. And then that's under 2P, and then under the mid-span load P, based on geometry, this will be 2 delta over 3. So I'll just mark, right, that this distance, that's based on this distance being 3L over 4, and this distance being L over 4. All right, so we have our external work is P times 2 delta over 3 plus 2P times delta. Internal strain energy. From segment 1, we have 2 mu theta 1. And from segment 2, we have mu theta 2. So here we'll note that theta 1 is equal to delta over 3L over 4, and theta 2 is equal to delta over L over 4. So theta 2 is equal to 3 times theta 1. So our internal strain energy then is going to be 2 mu theta 1, and we can write both of them, both terms in terms of theta 1, plus 3 mu times theta 1. And then plugging in our delta and L term for theta 1, we get internal strain energy as 5 mu times delta times 4L over 3. So then setting our internal strain energy equal to work. We solve for PU and get 2.5 MU over L. Questions?
So because this is a lower ultimate load, this mechanism's gonna be reached first and therefore happen
Yep.
more likely.
Exactly, yeah, because this one's lower than that one, this mechanism will occur before that one. We have one more to check.
Which is the hinge under each point load?
Exactly. Yeah, so if we have a hinge that occurs at P and then a hinge that occurs at 2P, right, it would have to look like this, because if there's no hinge at the fixed end, then, right, this segment will remain intact, if you will, or, it won't be compromised. So this is how the beam will fail. And intuitively, you might suspect that this will not be the failure mechanism, and we'll see that that's correct, but we'll go through the process anyway. So here we've got our L over 2, and then these are each L over 4. We'll note we have MU at the plastic hinges. We have theta 1 and theta 2, and this time they are going to be equal. And then we have our distance delta. So work is equal to 2P delta, that's it. Internal strain energy is 2MU theta 1 plus 1MU theta 2. Theta 1 and theta 2 are the same, so we'll call them delta over L over 4, or theta. So internal strain energy then becomes 3MU theta, or in terms of delta and L, 3MU times 4 delta over L. And then for our energy balance, we get PU is equal to 6MU over L. So by a long shot, this is not going to be your failure mechanism. So this one we can conclude is your collapse mechanism, being the lowest ultimate, or the lowest value of P to cause collapse. All right, we actually made it a little bit farther in today's lecture than I thought we would, so that's good. And this is a pretty good stopping point. The last page is just verifying or demonstrating each of these options with equilibrium and showing how you can rule out different mechanisms, because if you sketch the moment diagrams based on these values of PU, you'll find a distribution that has values of moment that are greater than MU. And so that tells you, like if you didn't figure it out from this, that will tell you this is not the correct mechanism. So that's why it's important to check with equilibrium, because sometimes you might make a mistake and pick the wrong one. So check it with equilibrium, and that will tell you if it's not the correct mechanism. And we'll touch on this next time, but basically for the first method, right, you would see a value greater than MU. For the true method, the maximum moment in that distribution would be MU, and so on. Right. All right. Any questions? All right. Well, good luck with the rest of your week, and I will